think this is probably a good place to start. Good time to start, I guess. All right, welcome to the stream. Let me get rid of the music. We don't need that. All right. So I've prepared something interesting today, I think. Like I was just talking to Chad about, we've gone over the one period model, where the stock can basically go up or down with some probability. Some probability p it'll go up, and then 1 minus p that it'll go down. And then in the last lesson, I think we extended this to a multi-period model where the stock starts out at some price S0 or S of 0, I think the second book likes to write. So the price at time 0, and then we said it could go up or down at each period. So it could either be, and we kept track of heads or tails as, we were pretending like we're flipping a coin. If it's heads, then it goes up. If it's tails, it goes down. Oh, I'm muted. Oh. Okay, let's make sure I'm not muted. I don't think I'm muted. Okay, so we started some S0. We have some S1, we flip a coin. If it's heads, the price of the stock goes up. If it's tails, it goes down. And then we just continued this model. We said that I am muted. You're not muted. Famished, you gotta refresh or something. Yeah, and then we just extended this to a multi-period model. So this was like S2 of heads, tails. S2 of heads, heads. And here it would be like I flip the coin twice and I get tails twice. And we'll put a ... here because, of course, you could just keep doing this forever, right? So you could have some S3. You could flip 3 coins, 4 coins. Every time you're flipping this, the possibilities are getting larger, spreading out, right? You could think in the limit, if you think of this period as like a period of time, and you think of the period of time, you're breaking up time into smaller and smaller increments, eventually you're going to get something that looks sort of like this infinite branching sort of thing, where it's just, I can sort of try to draw it, but I'm probably doing this part wrong. But you get the idea where, the possibilities are, you have this binary tree because at every point you have 2 possibilities, up or down. Right. So that's sort of where we're at here. This was the multi-period model that we talked about last time. And is there any questions about that before I go on? So, and then we had equations for all of the numbers. Like we said, if we had an option, there was a way to compute the price from the tree. There was also a bunch of delta computations that you could get from this. And there's like a bunch of other quantities like gamma and stuff you could try to estimate. All right, well, Famished, everyone else is saying I'm not muted, so I guess it's something on your end. I don't know how to help you with the mute. I think I'm good. I'm not getting any dropped frames or anything. Okay, so everything's good. Okay, so this was the multi-period model. And we'll be looking at a book, the second book of Shreve. So this is Shreve. And the book is, I think it's just Stochastic Calculus for Finance 2, and then ... continuous time models. Sorry about this. Let me erase all this other stuff. So continuous time models. This is the the second Shreve book. And I wanted to go through, I didn't want to go through every like part of the proof where he proves this statement we're about to write, but I did want to at least write the statement and give you some important facts about two of the cases. So we're going to have we'll be looking at the random variable itself and then the random variable, the log of it. And I just want to point out some very important compare and contrast between the two. All right, yeah, Famished is being a troll. Let's see. Right. So the idea here is now we're going to take the multi-period model and we're going to be thinking of the periods that are going by as some like infinitesimally small period of time. And we're going to let the periods go to infinity, the number of periods. So we're the idea is hopefully that if we break our time period into enough periods, that our model will be getting closer and closer to like a good estimate for like a continuous stock movement, basically. Right, so this is the second Shreve book, Continuous Time Models. This is Stochastic Calculus for Finance 2. And 3.2.7, he starts going into, I think there might actually be somewhere in the first book where he does this calculation also, but when I went through the book, I couldn't find it. So I found it in the second book, where he proves that if you take a the multi-period model and you let n go to infinity, that what you're getting is basically a normally distributed variable for the log of s of 0. So I'll say that again in a second, but let me just write the setup for the multi-period model. Basically, we're going to to make things simpler, we're going to assume that the risk-free interest rate is 0. That the up factor, like how much the stock goes up in the case of flipping heads, is 1 plus sigma over square root n. And there's a down factor, which is 1 minus sigma over square root of n. And so again, just to remind you that every time the stock goes up, we're going to multiply by u whatever, or it'll just be, we'll multiply by un, so it'll be like un s0 if it goes up, and it'll be dn s0 if it goes down. And then again, it can go up or down, and every time it goes up, we'll be multiplying by un. Every time it goes down, we'll be multiplying by dn. And then you can do your calculation here. Remember, there was like a risk neutral p, where we took, I think the formula was like 1 minus, what is the formula? I didn't write it down, but I think it's, who remembers the formula in the chat? I think it was 1 minus 1 plus r over u minus d. No, 1 plus r plus d or minus d. Who remembers? Well, whatever it is, I think it has to come out to 1/2 for this, so maybe that gives you a hint. I think there's a minus d here though, but 1 plus r minus d over u minus d? Yeah, that's got to be it, right? Yeah, where is Jeff? Okay, so I think this is correct. I think I remembered it correctly, and then the risk neutral q has to also be 1/2 because it needs to be 1 minus the p. All right, so in this multi-period model, basically in the risk neutral measure, we have a 1/2 chance of going up every time and a 1/2 chance of going down every time, and every time we go up by this factor of 1 plus sigma over square root of n. Every time we go down, we multiply by a factor of 1 minus sigma over square root of n. P is 1 plus r minus d over u minus d. Okay, so I think I got it, right? Yeah, okay. Okay, so they're both 1/2. So basically we're setting up this particular model, but I think you can actually prove that when r is not 0 and you have different u's and d's, I think you can also show that this same theorem holds. You just might have like a different mean and standard deviation for the result. But essentially what we're going to show is if we take the number of periods, like we were saying, and just take it to some really, really large number, eventually what's going to happen is because we're multiplying by these things each time, and because we're multiplying by these things each time, and there's some sort of central limit theorem thing going on, but because we're multiplying, we need to look at the log of it. But if you look at the log of it, then the log is normally distributed. So there's like a central limit theorem going on here, but for the log of s, the s variable. Okay, so yeah, so in this case, when n goes to infinity, the theorem is that s n of t, or actually log of this, is normally distributed. So this is log base e. I'll just write log, but it's log base e. So the log of Sn of t. Do I need a t? Yeah, I guess, what do I mean by t? Oh, yeah, I guess t is just the period, right? Yeah, so log Sn of t is normally distributed. And so if it's normally distributed, we should say what is the mean and what is the standard deviation, right? Because those determine, for a normal distribution, that's basically all the information you need. So it's normally distributed. What's the mean for the log of the variable? It's log S0, and we'll look at this in a second, but it's log S0 minus 1/2 sigma squared t, and then the variance is sigma squared t. Okay. So one thing to point out is that it's normally distributed, but the mean is not just the log of S0. Remember we said there's this Jensen inequality. So just because the mean for every period is a mean of 0, because the 1/2 and 1/2 here, the log variable still has a mean that's pulled down lower than the log of S0. So that's very important here. Yeah, I don't know, Famish. I don't know what to tell you. Okay, so does anybody have questions about this? This is a very important statement. It says that the original variable, even though the mean for a change over each period was 0, the log of the variable is normally distributed, but the sort of when we take the log of the variable, it lowered the mean. So we actually lowered the mean by this extra term, this 1/2 sigma squared t. But the variance is sort of like what we would expect. It's still just, sigma squared t. But also notice that as the time goes out, the variance is increasing. So you could think of that as being like the uncertainty of the stock is increasing as you go out in time, because it might go up or down like more chaotically the more time you have, right? Did you show this in the last stream, or is this new? Yeah, this is new. I haven't showed this in the last stream. No, this is all new. Yeah, this is in 3.27. I haven't talked about this second book yet, the continuous time model. So this is the first time I'm referencing it. So yeah, they do a lot of other continuous time stuff and stochastic differential equation stuff, but I think it's a little bit too advanced to just jump into that. So I'm just going to 3.27 when he goes from proving this multi-period model basically converges to be normally distributed. Or at least the log of it does, right? And this is very important that it's the log, and that's because we're multiplying by these things. If we were just adding these, then it would just be normal already. Okay. So I just wanted to compare and contrast this log, the log of the variable, the log of the random variable with the random variable itself, because they have two very different distributions. The fact that we're multiplying these randomly, it actually skews the distribution up because you could get a lot of sequences of ups, and because you're multiplying, they they compound. So yeah, let's look at the two distributions and let's look at their shapes as well. So we have Sn of t and we have the log of Sn of t. So they're both random variables. They're obviously related. One is the log of the other one. But because of Jensen's inequality, this log will change, our mean here. So it actually lowers the mean. Okay, any questions about this? Hello, Kyler. Welcome to the chat. So we're looking at a random variable. It's a multi-period model. We extended the number of periods to infinity, and we're saying that as n goes to infinity, the log of this random variable for the multi-period model, as we go out some time t, some number of periods, the log of it is normally distributed. And because we're taking a log, it actually lowers the mean somewhat, and we get this extra negative term here. All right. Maybe I should have left. Oh no, I'm gonna kind of rewrite it in a second, but. Okay, so yeah, let's just compare and contrast. So on one side we have S of t, or maybe I could even write just Sn of t for one of these finite multi-period models. Or we could think of S of t as like the limit, but let's just worry about Sn of t. And then we have log Sn of t. Okay, so this is the first one is the variable where the random changes are multiplicative. So it's, we're multiplying by something that raises the value or possibly lowers the value. But the multiplication part is important. So this distribution is what we call log normally distributed. At least in the limit, of course. Right, like if you take n to infinity, yeah, and you take these periods to be smaller and smaller in time, then basically what happens is you get this distribution that looks something like this. You have most of the values around here, and then there's some large skew here. Maybe I drew it badly. Let me redraw that. Maybe something more like that. So there's this large right skew. Oops, skew. Right, and where does this, I probably drew this like sideways. No, it looks all right. But where does this skew come from? Again, I was saying this, I kind of hinted at this before. I said, it's possible we get a lot of like up, it's possible we flipped heads a bunch of times in a row. Of course, the more times in a row, the less likely it is, but it's still possible. And because these values are multiplying each time, we're multiplying by that un value. If we get a lot of heads in a row, the value could get, extremely high. Like you could just be multiplying by some number over and over again. Maybe you flip 10 or 20 heads in a row, right? It's pretty unlikely, but in that case, the value of the stock would be getting very high. So there's a very low chance, but there's still some chance that you get these very large values occasionally. And so it's a very large right skewed distribution. One of the interesting things is, so what is the mean? What do people think the mean is of the distribution? So remember, in the risk neutral measure, the p hat was, or the p tilde was 1/2, and the q tilde was also 1/2. So for every period, what is the mean change of the stock in the risk neutral measure, where p hat or p tilde is 1/2 and q tilde is also 1/2. Right, so what do we think the mean is here for this distribution, right? We're starting at some S0 and then we're going out randomly and then we end up at Sn of t here. Right? Either going up or down each period. Remember p hat was, or p tilde was 1/2, q tilde was 1/2, right? And the up value, the up value was like 1 plus sigma over, square root of n, and then 1 minus sigma square root of n was the down. And I'll just say over here we already said this was normally distributed. And we talked about the mean for a second. But yeah, so what are the means for both of these? I guess I'll just ask both. Well, we already wrote it down for the last one, but hello, slight GPX2. Okay, so anyone that just joined, we're talking about continuous time models. Last time we talked multi-period model. Now we're letting n basically go to infinity, the number of periods. And we said that this Sn of t random variable that's supposed to represent like some stock that can go up or down, this was log normally distributed, and we're trying to think of what is the mean of, at time t, what is the mean? And then also we have the log of the random variable, and we said that this is actually just normally distributed, and we kind of wrote down the mean before, but I erased it. So yeah, we really want to compare, I just want to emphasize that we want to compare this to this. That will be an interesting comparison, because here we have the regular variable, and here we've transformed it by some non-trivial function that has concavity to it. So there's a Jensen relationship going on basically, because Jensen's inequality says that if you apply a concave function here to a random variable that's negative concavity, or the second derivative is negative, then whatever the mean of this random variable is, this one should be lower than the log of this one. So log should kind of lower, the mean of the log variable should be lower than the log of the expected value of the original variable. Just hopped in to say you're the best. Cheers. Thank you. I appreciate that, really. Any guesses from chat? So in the risk neutral measure for this Sn of t, we had 1/2 chance of going up, 1/2 chance of going down, and the up factor was actually, if you average the up factor and the down factor, they averaged out to 0. So actually the mean here is the same as the starting value. In fact, I think this one is a martingale, so the expected value at time t is just the value of the stock at time 0. So the mean is just S0 here. Or S of 0, whatever. Yeah, maybe I should be consistent with the notation. I guess technically it's Sn of 0, yeah. Right, so that's saying that this random variable that's supposed to be representing like the stock changes, the stock price changes in the risk neutral measure. If I want to know what's the expected value at time t, well, I just have to look at what's the stock value right now, and that's my best guess of what it will be at time t. In fact, the expected value at time t is just Sn of 0, the time now. Okay, but yeah, what is the mean over here though? We kind of wrote it down before. We said that it's normally distributed, and the mean was log S0 minus some value, right? It was log Sn of 0 and then minus what was it, sigma squared t, right? Yeah. Okay, so again, just pointing out that the mean here at time t is just the stock value at time 0. But in the log, if you change sort of, you can think of it as like a change of coordinates, but it's like a non-linear change of coordinates. So in this change of coordinates, the distribution of the Sn of t's is now normally distributed in this log way of looking at things. But what we did to the mean was we didn't just get the log of Sn of 0 as the mean, we got log Sn of 0 minus this extra thing. But interestingly enough, if sigma is 0, then it is the same. But sigma 0 is very not interesting, because if sigma is 0, then it's just a deterministic function, then obviously the mean will just be the log, right? So in any interesting case where sigma is not 0, then this mean is actually lowered by sigma. And of course t is not 0 as well. Can you buy a fraction of a stock? Yeah, sure. In I think Robinhood, they let you buy, I think you can buy like 0.0001 share of some stocks. A lot of the expensive ETFs are like thousands of dollars, so sometimes they'll let you buy like, you know, 1,000th of a share for $1, but I don't know. It's all just, you just have to keep track of all the math on their internal ledger, basically, right? Like they can, as long as they have the share, they can divvy it up in their computer as much as they want in fractions. Yes, yeah, right. That's a good point. I'm writing it a little bit differently than the book, and that's because I didn't introduce this W of t, and I don't really want to talk about it yet. But yeah, I am writing it a little bit different. Yeah. Can I draw a graphic of log Sn? Yeah, that's a good point. Let me or actually let me just finish this table real quick, and then yeah, we can kind of draw some pictures. That's a good point. So yeah, this one on the left, without taking the log, this has a large right skew, but of course the normal distribution is symmetric. So over here, if we look at the log of the variable, this will just be symmetric normal. You know, so the mean is like directly down the middle. This mean could be like somewhere over here somewhere, but actually this value right here, the log of S0, that's actually the median. Or actually, I don't want to get into it now, but the median is, yeah, the median is like somewhere over here. Yeah. But I just want to point out the fact that the median and the mean are not the same, right? So over here, the mean and the median are the same. This is normal. It's symmetric completely. Its mean is log Sn of 0 minus 1/2 sigma squared t. And the variance is also just, well, I guess the standard deviation would just be sigma square root of t. Yeah, Mavurt is pointing out that this is very, very similar to theorem, or I mean, it essentially is theorem 3.2.2 in the book, but I'm writing it a little bit differently because I'm not using the notation W of t. W of t they use later as notation for Brownian motion, and I just basically don't want to get it into any of that just yet, so I'm kind of stating it a little bit different. Actually, I'm going to state 3.2.2, but yeah, we'll state it in our way without W of t, basically. So, and then yeah, somebody asked if I could draw a graphic. So, I mean, this is sort of like your best graphic here. You're starting out, you could think you're somewhere at S0, actually. You gotta be careful where S0 is, but yeah, I think S0 would be right here. Yeah, if this is the mean, this would be S0. And then as you go out in time, you could think of this as like, no, this is bad. Yeah, I'll just draw it. Yeah, it's hard to see it from here. I'll just draw a better graph, or a better picture, I mean. Okay, so literally it'll look something like this. So here's S0, or here's S of t, Sn of t. So we have S0 of, or Sn of 0. up factor, down factor. The only thing is that, like what I said, when the up factors get larger, when I'm multiplying by a number, the largeness is actually compounding. So if I want to be really technical, as I get lower in the tree, these things should be getting thinner. And as I get higher in the tree, they should be getting wider. So something like that. Yeah. I mean, not the best picture, but I think it gets the point across that these are getting wider as the up factors compound, and these are getting actually skinnier as the down factors compound negatively. As you keep multiplying by down factors, this difference gets smaller and smaller, right? So this is the Sn variable, and that's why it has this skewed distribution in the end, where you have most of the values are going to end up right around here, and then you're going to have this large skew, right skew here. And that has to do with these up factors compounding. Of course, in the log variable, if you transform everything in this picture, so you just take this whole picture and apply log to everything, then you get log Sn of 0 at the bottom. But now the up and down factors in the log scale are actually adding or subtracting the same amount. So in here, the graph is actually perfectly symmetric. And that's why in the end, if you extend this out the same way, which I'm probably not doing properly, but in the end you'll get something that's just perfectly symmetric, normally distributed. All right, so this is right skewed. Hopefully this picture is conveying something important to you guys. Does that make sense? Everybody in chat? So the Sn variable, because we're multiplying these un and dn factors up and down, the up factors tend to create a bigger difference as you keep going up. The down factors actually get skinnier, so you end up getting this big right tail to the distribution, which corresponds to possibly getting a lot of heads. But then in the log transformed variable, now the up and down multiplications actually just become pluses or minuses that are the same value, either plus or minus. And so going up or down is symmetric, and there's no difference there's not the same, there's not this compounding of the uns or compounding of the dn's. You just get, in the log transformation, everything's just symmetric, and the theorem we just sort of stated was that this is distributed normally. Okay. Yeah, does anybody have anything to say about this? So I'm trying to give you a little bit better conceptual picture of what's going on by drawing these pictures. Of course, I'm not being super formal here, but everything I'm saying here you could turn it into something formal if you wanted to. Okay, cool. All right, yeah, so then I wanted to jump to 3.2.2 on page 92, like Mavort is stating there in chat. So yeah, I'll state it slightly. Actually, no, I'm going to state it the way the book states it. Actually, yeah, no, everything's fine. This will just be like a more formal version of what we've already been saying. Yeah, so this is theorem 3.2.2. And it says, as n goes to infinity, as the number of periods in our multi-period model gets larger and larger, the distribution of Sn of t converges. So the book used a little bit different terminology, but I think it's actually more precise to say it converges in distribution, so I'm going to write it that way. Although maybe I'm wrong and this is just stupid, but I think this is the right way to say it. This is the more common way I'm used to phrasing it. So converges in distribution which basically just means that I think you could show that it's equivalent to like the characteristic functions converging pointwise, or that basically the probability density functions are equal up to like some net measure zero set, I think, in the limit, something like that. The distribution of Sn of t converges in distribution to S of t, which is a new random variable defined for all values of t, not just at the integers. And it starts at S0, and then it's an exponential function applied to basically this Brownian motion, which is just some normally distributed variable with variance sigma, or sigma squared. Wt is just a standard normally distributed variable, so it has mean 0 and standard deviation square root of t, or variance t. And then minus 1/2 sigma squared t. And this is also very important part, this minus 1/2 sigma squared t. That means that the variance of our Brownian motion is essentially compounding in a negative way. So we're actually losing, over time, we're actually losing, exponential growth based on this volatility. This is a very, very, I would say probably the most important concept in finance, especially that people don't really understand initially. So this factor right here is literally, let's just like highlight this in our notes or something. This is saying that, or I'll put it in quotes here, but this is saying that the variance or the volatility of the stock, and I'll put this in big caps, slows the long-term growth of the stock. Meaning that the more volatility that you have in your stock, well, we don't see it in the equation here, but there's actually a part for where the stock can actually be going up in value, and that will be adding a term here, but we still are getting this minus term. So if the mean stays the same and the volatility increases, then it's slowing down our long-term growth because we're exponentially increasing at a lower rate based on, as time goes by, this increases, right? So I would say, end quotes here, I would say this is, if you want to take away anything from all the videos that you watched in finance here, this would probably be the most important statement here, that in the limit here, this geometric Brownian motion in the risk neutral measure is converging to this, basically this exponential, which is varying randomly, starting at S0, but it's accumulating this negative part based on how much volatility there is. And over time, it's actually accumulating more and more. So if you're not, you could think of it in other words, if you're not getting more return for your stock, then you shouldn't take on more risk. And I think we've already seen this in some of the other stuff we've looked at where, like the increase, if you look at the Sharpe ratio, or remember we were calculating like Kelly leverage, like the ideal leverage you would want on the stock. You always wanted to put less money in the stocks that were more volatile. And this is like an explicit way of seeing that if it's more volatile, it's going to be bigger negative number here, right? So your stock is going to be going up exponentially at a lower rate over time, which is going to hurt your stock, of course, if you're not getting good returns. Like for the stock we did, the R was 0, right? The risk-free rate was 0, so we expected our stock to not go up at all on average, right? And in fact, the long-term exponential growth rate is actually negative, because this has mean 0, right? So the mean of the exponential part is actually negative. And that's the same thing as the last statement we said before. Okay, is there any questions about that? I think this, like I said, this is very, very important. So if anybody has any questions about this, I would speak up or forever hold your peace. Is that the I don't know. Let's see if I can grab water. Oh, I got a little bit of water. So any questions about that, guys? So you could say that this is sort of like the solution to some stochastic differential equation where it's also the, the limiting distribution of that finite model as well. So we haven't really written down what the stochastic differential equation is that this is solving, but you can sort of see how this is similar to our normal differential equations, right? Like what actually I'll let you guys, this is a good question for the audience. What does this solution remind you of in terms of ordinary differential equations? So we have an ordinary differential equation. It has a solution that looks very similar to this, but it's not sarcastic. Sarcastic. It's not stochastic. Does anybody know what differential equation I'm thinking of? This should be an easy one, right? Are there stocks that give less return than bank interests? Well, if there was, Rex, and they told you they were going to give you less than the bank interest, then you probably wouldn't invest in them, right? So there are stocks that have lower return than the risk-free rate, but they're not going to tell you that that's the case beforehand, right? Obviously, every company thinks they're going to be making more money than the risk-free rate, or else no one would invest with them, right? Like if my whole business plan is just take everybody's money and invest it in treasury bonds, then probably that's not a good business plan because no one needs me to do that, right? Everyone else can just do that on their own. All right, no guesses. So, all right, what I was trying to get at for the differential equation was we have the differential equation, which is just dy dx equals y, right? I want to separate. I wrote this in a different color because this has nothing to do with this, okay? But we know this differential equation from ODEs, right? This is basically like your most basic non-trivial differential equation that has like a y in it, right? So dy dx equals y. We know the solution is y equals e to the x, right? Because this is saying that e to the x is its own derivative, and it has, we can add a constant in the beginning. But I just wanted to point out that the solution to this differential equation looks very similar to this, minus the randomness, where we have like some constant times like e to the x, except this time it's e to the, something with a t in it. Right, so essentially we can write down a stochastic version of a differential equation that we think, our stock essentially satisfies, and this is the solution to that differential equation, or stochastic differential equation. Can you give geometric intuition so you have stochastic smooth deformations of some manifold? I mean, that's probably above my pay grade. I've studied manifolds, I've studied algebra, but I never studied like random deformations of a manifold, for instance. Can you explain what the W of t is? Right, yeah, sorry, I'll write that. I forgot to write that. Thank you, Maverick. Right, I said it when I was writing it, but I didn't write it down. Yeah, this is just going to be a random variable. So W of t is approximately, is normally distributed, and it has mean 0 and variance t, yeah. Okay, so this is the variance, not the standard deviation. So the standard deviation is actually square root of t, and the mean is 0. So what this means is that, remember, when you take the log of everything, then it's normally distributed, and it has mean, yeah. Oh, wait, I'm leaving something out here, aren't I? Yeah, I'm leaving out, oh, no, this is right? Yeah, okay, never mind. Yeah, okay, we're good. Yeah, so W of t is just a random variable. It's normally distributed, mean 0, and variance t. So as t gets bigger, the amount of randomness, the variance increases. Thanks for helping me with that. Okay, so any other questions about this? So this is saying that we're, the limit of the multi-period model is essentially, well, if you read more of the book, you would see that it's a solution to some stochastic version of a differential equation, which is very similar to this. And the solution is also some exponential, just like it is for this one, except there's this random component to the exponential, which is you have some random variable, but it's changing it's changing with a normal distribution. Okay, let's see, how much time do we have? Got some time. Yeah, so a lot of this, unfortunately though, at least from what I've seen, a lot of the SDEs, the stochastic differential equations, are sort of hard to solve except for in like special cases. This just happens to be a special case where there's a nice solution. But no matter it's kind of like for ODEs where even if you don't have a solution, you can still estimate it. Like actually, Mavort was estimating using Euler's method for ODEs, right? There's something that's like extremely, extremely similar where you can take an SDE and you can create like a random path that's sort of a solution, or at least in the limit, it would be a solution to the stochastic differential equations. So I would say it's very, very analogous to Euler's method, except at each step, instead of going in the direction of the derivative, you're just going to apply some like random perturbation, and then you just keep doing that. And the random perturbation will be, according to whatever the stochastic differential equation that governs the system tells you that, the variance should be at that point, or the mean, etc. Is W of t is like the frequency of random oscillations? Could you say it like that? Is W of t is like the frequency of random oscillations? I wouldn't say it frequency. I think frequency is probably the wrong word. I would just say that W of t is some random perturbation that's normally distributed. It can either go up, it could go down. The mean is 0 though, so on average it's not going to go up or down. But yeah, you just want to think of this as like some random push up or down. You can think of it even as like wind. Like Brownian motion originally was used to describe like a particle in the air. So you could think it's just some random small push in like one direction or the other. But we're only in like one-dimensional space, so it's just either up or down. Euler, yeah, I can't say this. Maruyama method. Yeah, that's the stochastic version of the Euler method. Yeah, exactly. Yep. Perfect. Yeah, it's very cool. I've done it. I've done a lot of simulations with it in like Python and stuff. It's very cool. You can simulate stocks, but also you can simulate other types of things. Things that have like certain types of drag, but are also randomly distributed. And yeah, I mean, it's very interesting. I would suggest looking up different stochastic differential equations that show up like in nature. One is obviously stocks, if you consider that nature. But there's other stuff like the volatility of a stock follows a different stochastic differential equation, for instance. And that's also a very interesting one. I forget the name. Maybe Maverick knows. But yeah, there's an SDE for like mean reverting processes. So things that move around randomly, but they revert back, like they get pulled back to some mean always. So that will be a different stochastic, a different SDE will govern that versus what governs stocks, like for this. Maverick says, so if w of t is a random variable, doesn't that mean that f of t is also a random variable? Yeah, of course. S of t is the price of the stock in the future. It's going to be random. Yeah, this is random. Yeah, we don't know what the stock will be at time t. It depends on what we basically have to flip almost like an infinite number of coins. Then we know what w of t is at the end. Once we've flipped all of those coins, then we know what S of t is, but all of those coin flips are, of course, random. So, and you could, the book talks about this, but you could think of w of t as like you're sort of going up or down by some amount, some infinitesimal amount, and you're doing it like infinitely many times. And so in the limit, you get this like central limit theorem that says it's converging to a normal distribution, and because we're allowing the increments over a period to be smaller and smaller, the variance actually only increases to just t, and it doesn't like go to infinity or something, for example. Rex says, I think Brownian motion was discovered when people looked at slides under a microscope. Yeah, I know it was something to do with that. I thought they were looking at like dust particles under a microscope or something, but maybe it was... I mean, you can see Brownian motion in things that are like lying in water, for example, because the random water currents will sort of, be moving like a particle of dust around. But that's more like a two-dimensional example. Can I prove the theorem? We could probably prove it next time. So I can go through the proof in the book. Yeah, so I actually started out kind of wanting to prove this, at least in the limit. We might just prove it next time. I think the proof in the first book, I actually liked it more. They proved it, I think, this is just me remembering, but I think they proved it using the convergence of the characteristic functions or of the moment generating functions, I think. And I liked that proof a lot. And here he proves it slightly differently, but I looked at the proof. I wasn't a huge fan, so I might try to prove it the other way, or if I can't prove it the other way, I might just write down his proof. But I just remember there being a nice proof. I think it's the general proof for the central limit theorem. Essentially, though, this is just going to essentially be the same proof as the central limit theorem. It's just the central limit theorem for this particular thing. So yeah, I guess to just kind of give you the cliff notes, the proof is essentially the same as the proof of the central limit theorem, because what's going on here is a central limit theorem. It's saying in the limit we get this Brownian motion, which is normally distributed, right? So it's essentially it's central limit theorem for the log of the variable. So you just prove that the log of the variable has this central limit theorem. It's normally distributed. It has this distribution, and then you just take e to the power to get back to this. So that's essentially the proof. We could do it next time. It's just a little convoluted, and I wanted to be able to talk about all this stuff a little bit more freely, so I didn't want to be completely bogged down by the proof. But yeah, I think we should do it next time. I wanted to do it this time, but I decided not to. Yeah, I think it is very important, but it's basically just as important as the central limit theorem in general, which is also very important, of course. But if you look up the proof for the central limit theorem, this is essentially the proof of the central limit theorem for the log of the variable. Yeah. Okay. Right, and then I kind of had this definition here. It's kind of a long definition. I'm not sure if I want to go through the whole thing. I'm not sure how useful it is, but, well, I guess they define Brownian motion, so I guess I should just write it out. Kind of an interesting definition. Rex says, Matt, you should have seen Maverick doing proofs. He was so good. Yeah, I was working yesterday. I had to do a job with a friend for some extra money, but yeah, I missed the stream. I was looking forward to that, but I actually wasn't home at the time. Okay, yeah, so just last thing I'm going to do, unless anybody has any questions about anything that we've talked about today, but I'm just going to write down the definition of what a Brownian motion is, like the full formal definition. The Brownian motion will have this distribution at time t, the standard Brownian motion. And so they use the same notation for Brownian motion. Brownian motion is just w of t. So it's kind of like overloading the notation a little bit, but W of t is this random variable that's normally distributed, but it's also a random process, which they end up defining as Brownian motion, which is this definition I'm about to write. No questions, please continue. Okay, cool. Yeah, so Mavor, let's do this proof beginning next time. We'll do this proof either one way, or I'll just follow the Shreve way in this theorem. One way or the other, yeah. We'll do the proof next time. I wanted to do it this time. I thought it would be too much if I went through the proof and then did all the other stuff as well. Okay, so last thing, just defining what Brownian motion is, this W of t thing, this mystery-looking W of t. So defining W of t as a process, meaning that it's like, changing as time goes on. So first of all, what does Brownian motion look like, right? You're getting these small, normally distributed increments, like random movements, right? So you get this sort of like rough looking process. It looks pretty much like a stock. If you look at the log of the stock value, that will look like Brownian motion, right? And it's just this, it could have some positive mean, negative mean, but you get these rough sort of paths. And you can actually prove that the function is nowhere differentiable with probability 1. So kind of an interesting result. I'm not going to prove that, but yeah, there is an interesting result for the stochastic processes that these Brownian motions are actually, there actually is some chance that they're differentiable, but that chance, if you look at the measure of the set that it could happen, it's actually size 0. So it could happen, but the probability is 0. Essentially, it could happen, but if you do more and more trials, the probability or the proportion that it happens, would get lower and lower. So almost all of the curves are nowhere differentiable. Oh, we got a band. Nice. Okay, so this is just defining, what is a Brownian motion. And the definition is very abstract, but I can kind of hold your hand through it for a second. So this is 3.1. And it just says, so we have a probability space, which is a sigma, I believe this is a sigma algebra. Am I saying this right? Oh, no, this is yeah, I think that's sigma algebra, right? All right, maybe I'm mixing up these two. Wait, what is F? Okay, so P I know is the probability measure. That's obvious. Yes, I mean this gotta be this. This is omega. This is our list of possible states. So for the finite multi-period model, it was just how many times you got heads, how many times you got tails, and every possible like head, tail, 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 head. That's all your possible states. Like everything that can possibly happen for the random whatever things that can happen randomly could happen. F, what is F? I'm trying to remember now. So we have our sigma algebra. F is, what is F? Well, maybe I'll know from the rest of this. Hold on. Trying to remember, what do we need for this stuff? Maybe somebody can remind me in chat. So we have all the possible states, like all the things that could happen. This is our probability measure. This is, so this is like saying for each one of these things, what's the probability, or some subset of these, what's the probability that they could have happened? This actually tells you the probability. And I'm just trying to remember what F is. Maybe Mavort could remind us. Yeah, what is F? What does F stand for? I'm trying to remember what F stands for. Okay, but basically it's saying we have, some random things that can occur, some way of measuring them, and if the following things happen, then we call this thing a Brownian motion. So if we have some random thing W of t, so random function, yeah, so let this be a probability space. So for each like possible sequence of events that could happen in here, so for each omega in little omega and big omega, suppose there is a continuous function w of t that satisfies so w of 0 is 0. So basically the thing starts out at 0. Some functional of entropy. No, I don't think that's it. So yeah, w starts at 0. W of 0 is 0. And for w of t, if I pick any sequence of time intervals, so I start out at t0, which is 0, and I go to t1, so on, all the way up to tm. So if I start at time 0 and I break my time increments into some, they don't have to be evenly spaced, just some time intervals here, then so suppose there's a continuous function, w of t, that satisfies w of 0 is 0, and for any breaking of the time intervals, the increments so basically like from wt of 0 to wt of 1, that is normally distributed, and then from wt of 1 to wt of 2, that's also normally distributed, and all of these increments, the difference in the w's is normally distributed. So basically the increments w of ti plus 1 minus w of ti are independent. It's a little, I told you it was a technical definition. So w of t I plus 1 minus w of ti, this is the difference, that w takes at some time interval. So these are all independent. The differences are independent of each other. And they're all normally distributed, and they have mean 0 and variance the difference in the time. So they're all independent and normally distributed. With, like I said, mean 0 and variance ti plus 1 minus ti. Oh, wait. Yeah. Oh, I wrote it wrong on my paper. Oh, no. Yeah, that's right. Okay. Yeah, I got it right. Okay. Yeah. I like to think about some gradient as color associated with graphic. So this functional shows will curvature diffuse or focus. Yeah, I don't think that's applicable to this. I don't think we're viewing, I can't remember what f is, but it's probably standing for a word that starts with an f. I don't think it's functional, or I'm trying to remember what the word is. So I'm trying to think of what I'm missing. I mean, we have the probability measure, we have the state space, which I'm pretty sure is just a sigma algebra. And then I don't know why I'm blanking on what f is. Or maybe f is the sigma algebra. Okay, yeah, I think f is the sigma algebra, and this is the state space. Yeah, so this is a collection of subsets of this, but it doesn't need to be all the subsets. So it's just some measurable subsets, and they have measure p. Okay, yeah, I think that's it. Maybe I'm wrong. F is the sigma. Okay, yeah, I got it at the last second. Yeah, so this is the state space. This is like all the possible things that could happen. F is the sigma algebra of the measurable things that can happen. Sometimes it's just the power set of this, like you just say every subset is measurable, but it can be smaller than the power set of this. And then yeah, probability measure is just some measure on this sigma algebra with this state space. Do I have that right, Maverick? I think that's right now, right? Okay, so this is just saying that if we have a function w that makes sense for each omega in omega, things that can happen in the state space. So the w is basically dependent on this random event. So it's a random function. Or once we pick the element of the state space, then it's not random anymore. But this thing is random. So you can think of this as a random function, or it's just a regular function dependent on this random thing. And we're saying that it's Brownian, we're calling it a Brownian motion if this w of t function exists for all t greater than or equal to 0. It has the property that w of 0 is 0. And for any time increment, the change in w over that time increment is normally distributed, independent, and it has a normal distribution with mean 0 and variance ti plus 1 minus ti. So it's a long-winded definition. I'm not sure exactly why. I think there would be an easier definition, so I'm not sure exactly why they go through the trouble of defining it this way, but the only thing I can think of is that this is a little bit more abstract, so it's sort of, I guess, a priori could involve more things, but then you prove actually it's, just this thing of this type. I feel like it's one of those definitions, but yeah, I maybe I'm wrong, but I feel like there's like an easier way to define Brownian motion, but maybe I'm wrong. I mean, whatever definition you're going to have for Brownian motion, it should have this property anyways. So that's kind of like the idea that they're basically defining it based on the properties that you want it to have, and then they prove that this thing is actually like unique. That if you have one of these WT functions, it depends on this, state space element. And then if all of these increments are independent and normally distributed with this, distribution, then there's basically only one thing it can be, and so we call that thing Brownian motion. At least in this one variable, but you could extend this to 2 variables, 3 variables, 4 dimensions, 5 dimensions, right? Of course, if you had a portfolio of multiple stocks and you're looking at the joint distribution of all the stocks, you're going to need Brownian motions with more dimensions than just one, right? So yeah, there's a way to extend this to more dimensions. The only difference is that instead of this difference being like normally distributed in the one variable case, it'll be like a multivariable normal distribution, right? So the increment changes will be normally distributed, but in the multivariable sense. Okay, I think that's all I got for today. So hopefully I'll remember. I think I'll remember, but let's try to prove that last theorem that we had on there, this theorem 3.2.2, that the limiting of the multi-period model actually does converge in distribution to this normal variable, at least in the log, right, when we change coordinates to the log space. Then it looks normal, and so I think we can probably prove that next time. The proof, you can look at the proof in Shreve under theorem 3.2.2, but without reading the rest of the book, it is a little bit weird. So I'm going to try to maybe convert it into just a general kind of like central limit theorem proof, maybe just using like the characteristic functions. And I think that will be a little bit more illustrative, because not only will we be like proving the theorem, but we'll be proving basically like the central limit theorem in general, which I think is cool. So kind of like hitting 2 birds with the same stone, if you want to think of it like that. So central limit theorem next time we'll prove, and we'll show that it's essentially the proof is like very similar to the proof of this 3.2.2. All right, I don't have anything else. That's basically all I wanted to talk about. So thanks for stopping by. We talked about single period model, multi-period model. Now we're talking about this continuous. Basically, as you let the number of periods go to infinity and you look at how this stock can change over smaller and smaller periods of time. This Brownian motion is what we use to model the log of the distribution, right? And then yeah, there's some Jensen stuff going on when we switch from the log space to the regular space, and it affects the skew and etc. Everything else I talked about. So internet did not drop once. Awesome. Yeah, I'm like thinking that it had to be something else was overloading my Wi-Fi router. I think maybe there was like some attacker on my network and they got into one of our devices or something and it was overloading the system because we changed the password now and so everything it should be wiped out for anyone that was using our router improperly. For what day is lesson 23 planned? That will be Tuesday. So lesson 23 on Tuesday. Tomorrow I'm just gonna do like an hour or two on my research stuff, which we're getting into like oprads and dealing with this graph homology complex stuff. Yeah, we got the recordings. Let me put the YouTube up here just in case anyone wants to see that. So you can check YouTube for any of the past videos if you are interested. I have them in the playlists. You can look at, you know, calculus, linear algebra. What else did I do? Now I've done so many videos I can't even remember. Calculus, linear algebra, probability, and group theory, right? So we're trying to hit all the major subjects. Hopefully I'll be into what I think I want to do some complex analysis eventually. Probably not next week, but maybe coming up. I think complex analysis will be fun. Like analytic functions, Taylor series, stuff like that. Okay, let me find someone to raid, but unless someone else has something interesting to say, I'm just gonna sign off soon.